All right, good afternoon, everybody. Welcome to the last session on the last day of Ignite. I hope you guys have had a great conference so far. My name is Jason Messer. You're going to be able to hear from Don Stanwyck and Paul Long as well as we talk to you about some of the improvements we've made in Windows Server 2016, both for software-defined networking, diagnostics, and monitoring, for a very fast data plane experience, high throughput, and also for some time sync improvements. And we'll also be joined up by some of our NIC vendor partners as well. So perhaps you've seen this slide multiple times this week, but Server 2016 really has a lot of positive investments, huge innovations that have been made in the areas of security, software-defined the data center, and the cloud-ready application platform. Things like shielded VMs, host guardian service, storage spaces direct, software-defined networking, and then containers, of course, are all huge investments we've made for Server 2016. So here's the agenda for today, because it is a bit of a hodgepodge of topics. We're going to talk about software-defined networking and the motivation behind it. I will then speak about monitoring and diagnostics for that SDN infrastructure. After that, Don Stanwyck will join me up here on stage, and he'll talk about our data plane, along with some of our NIC vendor partners, and then Paul Long will finish up with the time sync improvements. All right, so data center networking can be very complex. We have multiple compute nodes, storage nodes inside of a rack, connected to top of rack switches, which in turn are connected to spine routers, what could be in turn connected to load balancers, firewalls, and then core routers. And so this is a very complex infrastructure to manage, let alone diagnose or troubleshoot when something goes wrong. Along with these challenges, we've noticed a few other challenges that customers have faced as we've been speaking with them in the past 2 or 3 years. First of all, they have the problem of agility. They really need to be able to deploy new workloads, bring up tenant VMs, set up applications very, very quickly. And sometimes the bottleneck can become the IT department, either because these services are unknown or because they have certain networking requirements that need to be satisfied through a separate network administrator. In addition, there's a lot of security risks associated with a modern data center today. Almost daily, you hear of new zero-day vulnerabilities, new exploits, new attacks that need to be mitigated against in a very quick manner. Lastly, we really have a lot of costs associated with all this physical gear. Switches are not cheap, load balancers are not cheap. And so that's one of the reasons why, or these are the 3 main reasons why, rather, we've brought a lot of the software-defined networking stack that's inspired by Azure to our on-prem customers in Windows Server 2016. Along with those challenges that we're attempting to solve, agility, security, and costs, we also have some foundational layers. Obviously, the system has to be reliable. We also have to have high performance for these workloads. And lastly, we do want to have some sort of troubleshooting steps, monitoring and diagnostic capabilities to keep the infrastructure up and running or bring it back to operational state as quickly as possible if something goes down. So let's dig into the monitoring and diagnostics that we have in 2016. So what happens when something goes wrong? We have a lot of different deployment dates, times, experiences, but we typically think of day 0, day 100, where day 0 is really the initial bring up of the fabric itself. After you have the software-defined networking fabric brought up, you want to start bringing on some workloads from tenants, either from different business units, departments, or if you're in a private cloud, a specific tenant, maybe running IIS web server, SQL, SharePoint, what have you. And then day 100 plus, is just the normal operation of this system. And so failures can happen, obviously, any time during these 3 stages that I've outlined. What we've done with SDN diagnostics is really wanting to expose as much actionable information as possible to the administrator so they can quickly take action to fix whatever went wrong. A lot of these things are lessons learned from our Hyper-V network virtualization stack in Windows Server 2012 R2. Perhaps some of you have deployed this and ran into some problems either with gateways or bad drivers or even data plane control path type of errors that we really need to be able to quickly identify and resolve those issues quickly. And so we've taken those lessons learned and we've kind of divided them up into a class of problems that we want to be able to diagnose. And we've been able to add some PowerShell commandlets and some other automatic tracing and monitoring infrastructure to be able to facilitate this. All right, so day 0. You have a brand new SDN infrastructure fabric, brand new Hyper-V host cluster. You're going to start bringing it up. You're going to start onboarding the network controller, onboarding the software load balancer, onboarding the gateways. In my session on Tuesday, I talked a little bit about this, from how we can go from 0 to SDN in under 60 minutes and bring up this complicated infrastructure in really under an hour. And so for this example, what we have basically in my setup back home is a set of 4 hosts. 3 hosts you can think of as running tenant workloads and some of the SDN infrastructure, while the other 4 are dedicated to fabric management with SQL Server, System Center Virtual Machine Manager, and also System Center Operations Manager. These systems are connected to the management logical network. First step, as I mentioned before, is to onboard the network controller, which is the brains behind our SDN infrastructure, to be able to define policy and have that policy pushed down and enforced on the data plane in the vSwitch. It does this through communication with host agents that are actually on the Hyper-V hosts themselves. That's the control path piece. Another piece of this infrastructure is the software load balancers. We also want to be able to extend access out of our virtual network to external clients, and then have those connections load balanced behind a set of back-end, what we call DIPs, dynamic IPs, serving the actual workloads themselves. Again, these have their own host agent that's able to communicate with the network controller and software load balancer muxes as well. The last piece of this infrastructure to bring up then is the gateways. Gateways perform a number of functions, including different types of tunneling technologies. We can create site-to-site tunnels between multiple sites or even into Azure using a site-to-site IPsec tunnel. Or if we are using GRE or perhaps MPLS, we can use a GRE tunnel to build that up as well. We also have a forwarding gateway, which allows us to route between the virtual space and the physical space. So this is our SDN infrastructure that's been brought up. Now, what happens when something goes wrong? One of the servers begins to have a bad day, or maybe one of the network controller nodes begins to have a bad day. Let's go ahead and take a look at some of the diagnostic capabilities that we can use to diagnose these types of problems. So I mentioned we have a set of PowerShell diagnostics that are both for the network controller, for the control path, and also for the Hyper-V network virtualization layer in the data path itself. I'm going to go ahead and run one diagnostic command that'll help us identify kind of the state of the system itself. This will go out to the network controller and actually query all the different fabric resources and some tenant resources to see what their configuration state is. And you can see we actually have some errors now in our deployment. We have software load balancer MUX that has an error or a failure reported, virtual server unreachable. We also have virtual networks that the policy configuration is unhappy for some reason. And we have some server resources up above saying that the SLB manager can't connect to this particular host agent, and similarly, the network controller can't connect to the host agent to configure virtual networking policy. So let's dig in a little deeper with this server resource and see what might be going on. I can actually narrow down, and just so I'm focusing on one set of fabric resources, I'm going to say servers and look at my server resource. Here I have a resource ID, which I need to figure out, okay, what actual server resource does that correspond to in the physical world? So I am going to grab that resource from the network controller and dump it out as a JSON object. By doing this, I'm able to actually determine what management IP address and what server this is interfacing to. There's a lot of JSON in here, but what we're really interested in is the management IP address. if I scroll up, I can see that the management address is SA18N30-3, which is one of my Hyper-V hosts. So this guy has a problem. I need to figure out why. So let's just see if it's pingable first. Go ahead and do a ping command. Well, that looks like it's up and running, so maybe the server is still connected to the network, but something's wrong with the communication between the network controller or the software load balancer and the different host agents on the system itself. So let's go ahead and go to this machine. 30-3 is right here. And this will simulate basically, if the connection was either offline because of network connectivity issues, if VLANs weren't trunked correctly, or just the host agents themselves weren't running. In this case, if we take a look, we can see that the NC host agent is stopped, as is our SLB host agent, which is critical pieces so that the network controller is able to push this policy and have it enforced through these host agents. Let's go ahead and bring these guys back up. The next step, when we're first bringing up the fabric, after we've confirmed that the servers themselves have connectivity to the network controller, we want to make sure the network controller is happy as well. We can also run some diagnostics on the network controller itself to see what its state is. So let me go ahead to one of my network controller nodes and take a look. I can do a command that will allow me to check the state of all of the different applications that make up the network controller. It's actually a multi-service application running on service fabric for high availability and resiliency. I'm going to go ahead and see what services are running and what their state are. Again, the network controller is made up of an SDN API surface for interaction, made up of a vSwitch service for pushing policies to the vSwitch, made up of gateways, so on and so forth. Now, all of these services look healthy. As we can see, the replica data is ready. And so we want to really dig in more and see if there's anything else wrong with any of the replicas. All this is telling us is the primary replica is up and running on these particular network controller nodes. So let's dig a little deeper. We'll check out the service fabric node status for one particular service, for the API service, for instance. Now, this gives us basically a WinDiff evolution of the state of the system itself. So we have a primary and secondary nodes, and you can see that the primary node is running on SA18, N30, NC1, it's ready. NC3 is an active secondary, which is also ready. But the replica status for NC2 is down for some reason. So we have some problem with the network controller, the second network controller node. Which again, if we have more failures, this will cause us to lose our control path, which we want to mitigate against. So let's go ahead and make sure we understand why this guy failed. So I'm going to go to VMM, through which I deployed this fabric, and take a look at the second network controller node. In the Services tab, you can see all the different, well, that's very small. You can see all the different services I have. You have software load balancer, production service, network controller production, RAS for the gateway production. So let's go ahead and zoom into the network controller. And again, this is just for demonstration purposes, but oh, the network controller node is down. I wonder who paused that. Let me go ahead and just resume that guy and make sure everything's healthy again. Now, this will give you an idea about the different services or the different diagnostics that we can do to figure out if a server is down, it can't communicate with the network controller, or if one of the network controller nodes is down, or one of the service members of the network controller application is not working for whatever reason. So let's continue on now. The next step, after we have our SDN Fabric infrastructure up and running, we want to be able to look at some tenant connectivity and onboarding some tenant VMs, workloads, services, and so forth. So you can envision now, again, we have these 4 hosts, and we have 2 green VMs from Green Tenants Virtual Network and 2 red VMs from Red Tenants Virtual Network, which we've deployed onto these hosts. We can also create load balancers for these tenant VIPs so that, again, external clients can access these virtual network resources through the software load balancer and have those requests load balanced between the available set of back-end DIPs. We can also do things like inbound and outbound NAT rules. If we want to give the green tenant access to an external network like the internet, we would create an outbound NAT rule so that they can access that. If we want to provide inbound NAT, maybe for an RDP session to a protected VM on this red tenant's network, we can also do that with an inbound NAT rule through the private VIP. Now the difference between these VIPs, virtual IP addresses, are that the public are actually publicly routable out to the rest of the world. Private VIPs are private to the data center. So we're able to get access into our virtual network through the software load balancer. But what happens if we have two tenant VMs which can't connect for some reason? They're having trouble communicating with each other. Let's go ahead and examine this scenario in a little bit more detail. So I'll go back to my demo machine, and we'll take a look at one of these tenant VMs. So this is the green web VM2, which I showed in the picture, trying to ping, just do a simple ping with the other green web VM. So let me zoom in on that so you can see a little bit better what's happening. This is a common issue we hear reported, is that tenant connectivity is a little bit intermittent. I mean, we're getting some packets through, but some we get requests timed out. So we want to kind of figure out, well, what's going wrong here? It looks like some of the traffic is passing, but some of it's not. So let's go ahead and check a look at this. One of the things that a tenant, or rather a host administrator, would want to do if a tenant reports this type of connectivity loss or intermittent connectivity is to actually examine their physical network first. Now, I alluded to this earlier in the picture, but we actually have one of our physical networks is called the HNV provider network. This is the network which is a transport for all the tenant network connectivity, the virtual network connectivity. It's critical that we have this HNV provider network up and running and connected across the host and the different layer 3 top of rack switches. We have another diagnostic tool which we're able to actually do a ping on this special logical network, the HNV provider network, to make sure that connectivity is up and running. So what I can do is go over to my VMM console again and take a look to see where this green web VM2 is running. Okay, it's running on node 3, and the node I was trying to ping was on green web VM1, which is running on node 2. So I want to make sure that the HNV provider network, that logical network between those two hosts, is up and running just fine. So to do that, I'm actually going to do another one of our diagnostic commandlets, get provider address, which is able to say which IP address from that HNV provider network has been assigned to this particular Hyper-V host, what the MAC address is, the subnet mask, gateway, and VLAN information as well. So I'm going to try to ping .66 and .67 from the other host to see if I do indeed have connectivity. Now I have some guilty knowledge about a particular command that we use to actually do this ping. We have a compartment that we hide the HNV provider NIC into. It's just a detail that this is why I'm using the -C3 option. It says ping from compartment 3. So I'm going to go ahead and ping. Let me first look at what the provider addresses are on this host, .64 and .65. So I want to make sure between all these different, this matrix of IP addresses, I'm able to have connectivity. So I'll go ahead and do this ping command to .67, which was a provider address on the other host from my .64 address. This guy looks healthy, so that's good. Let's go ahead and check from the other provider address. Again, this ping looks like it's healthy. Latency is low, and every ping's returned. Let's take a look, though, at a different IP address that's assigned to that other Hyper-V host. Okay, this one looks healthy. Now I'm wondering if let me check something real quick behind the scenes. Some of this might be because I am actually wanting to make sure that I'm on the right VLAN. The HMV provider network itself is going to be dedicated to a specific VLAN and a subnet prefix to it. So if my network administrator came in and changed one of the VLANs without me knowing, I might have a problem here. So that's what I'm investigating. Let me go ahead and try my ping again. Maybe I'm using the wrong. 66. Okay. So there's some connectivity issue that we can see here where the request is timing out for some reason. And again, I kind of alluded to this and gave away what it was, but it's actually a VLAN misconfiguration. But this is another common problem that can manifest itself by tenant VMs having intermittent connectivity because something's going wrong on the physical network itself. In this case, again, it's a VLAN misconfiguration. So let me go ahead and take a look at that and see what VLANs are being trunked to these particular physical network cards. And I see that instead of being in trunk mode, I actually have VLAN ID 7. VLAN ID 7 in my infrastructure is actually the management network, when in fact I need to trunk multiple ports into the Hyper-V switch. I need to trunk the management network, any storage networks I might have, and also the HMV provider network. So let me go ahead and fix that and see if this remediates our problem with tenant connectivity. Go back to my tenant VM. And now when I do a ping, sorry? Oh. Thank you. Come back. Okay. So again, you can see that basically we used our diagnostic command list to figure out what the underlying network IP addresses were for that transport of virtual network traffic, what VLANs they were on. And we then did some additional diagnostics and troubleshooting to see why we couldn't ping that tenant. And it turned out it was just a simple misconfiguration of a VLAN. Let's go ahead and go back to slides. Now we're at day 100. So we've brought up some tenants, or we brought up the fabric rather first on day 0, brought up some tenants and onboarded them, and now we're during some normal usage time. What we want to be able to do is really catch problems before they occur, right? Before any degradation happens, we want to be able to catch them. And it really starts with knowledge about what resources we have available to monitor and how we can monitor those. And we need actionable information to actually take a look at this. So to do this, we use System Center Operations Manager, where we've actually created an SDN monitoring pack for SCOM so that we can monitor these fabric and tenant resources. Now again, this is a work in progress. We are continuing to continuing to make the SCOM management pack better, rather. So we have a set of monitorable resources and some unmonitorable resources too that we should be aware of. If you've used SCOM before, you're probably familiar with the alerts view, different stamp views of the system itself, and how to resolve any of the alerts that come in. Let's go ahead and take a look at the management pack that we have for SDN. So here, we have a stamp view of the system itself, and I apologize the font's so small. But you can see under here that we have the SDN monitoring pack, and we have a set of resources that we're able to monitor with an alerts view, and also a stamp view, which gives us the entire system up front to kind of see what the health of the state is right now. And so we have access control lists, gateway pools, host groups, load balancers, all these different interfaces. Some of them are healthy, some of them are not healthy. For instance, the load balancer, if I scroll down here, we can actually see that one of these 3 load balancer muxes is not healthy. So if we want to investigate that further, we can take a look at the resource. And we see that the resource is this GUID string. Again, we're going to make this better so that it's not a 2-step process to figure out what the actual MUX VM is in the future. But for right now, you can still query the network controller interface and see which MUX this corresponds to. So again, guilty knowledge. I know that this MUX VM happens to be paused. So I'm going to go ahead and unpause it so that it can remain healthy again. Let's see, resume. Yep. I can go back to SCOM now, take a look at my alerts, and at least resolve one of the alerts that may be causing this problem. I can close it or set the resolution state to resolved. So again, that gives you kind of some basic ideas about the functionality of the monitoring pack that we're developing. Lastly, just leave you with kind of a troubleshooting workflow. Really, the process begins with triaging, then root cause, fixing, and monitoring, continuous monitoring with SCOM. We have a lot of great resources that we've published on TechNet for these diagnostic commandlets, as well as some scripts that are on GitHub, which I would encourage everybody, if you're using the SDN fabric, to contribute to as well. And then finally, some troubleshooting guidance on TechNet itself. And so with that, I'm going to go ahead and turn it over to Don, who's going to talk about the data plane.
Thank you, Jason. I hope you all got a lot out of that. Not only are we wowing the world with our new SDN capabilities, but they don't come without the tools you need to manage them, and that's a very important piece. We're going to switch topics kind of completely now from all that wonderful stuff we've built above Hyper-V to all that networking that's down in the bits and bytes. So hopefully that's something you're interested in too. Okay, we're going to talk about some data plane components. What are offloads? I need some interaction here. What are offloads? They're things we stick in the NIC. We make the NIC do work for us to accelerate our performance. Okay, how's that different from a feature? I'm not getting a lot of reaction here. Features are things that we put in the OS, okay? So there are things that we ask the NIC to do, and there are things that we build in the software of the OS. A lot of times we have pieces that we build together, where we make use of NIC capabilities to provide us the ability to work better in the OS. So, are offloads parts of all the features? No. We have features that don't use offloads. Features like NIC teaming, which don't care what the OS might be. I mean, what the NIC might be, or what its capabilities are. But we also have features like VMQ and VMMQ that make use of the NIC's offloads. And then we have things that just the NIC does for us. So here's a list, and I'm not going to go through it, but here's a list of some of the common offloads that we have in Server 2016. The good news is, today, our very rich ecosystem, and later in my talk, I'm going to have representatives of 2 of our NIC vendors up here doing demos. Our very rich ecosystem today says that virtually all of the offloads are available from nearly every vendor. Our IHVs have really stepped up to the plate and have provided us with what we need to run 2016 in a highly performant manner. And for that, I can only say thank you. Okay, so what are the new features in 2016? What are the data plane features? Well, first of all, we have all the kinds of things that we've had in the past. Access control lists inside the Hyper-V switch, bandwidth management of various different ways, Hyper-V network virtualization, which in the past we had in 2012 R2 with just NVGRE. We have a completely new version in our SDN forwarding extension that allows us to do both NVGRE and VXLAN, making use of the offloads that are in the NICs. We have NIC teaming. We have a new variety that's built into the switch. We'll get into that more later. RDMA, RSS, which I know you're all familiar with. TCP chimney offload, which maybe you're not, and that's okay. You can stay that way. Virtual RSS, which we'll talk more about. VLANs, VMMQ, VMQ are all things. VMQ you're very familiar with. VMMQ you will know before the end of the day. Does it all work together? Not quite. Because you see, well, let me wait for the right slide. Okay, so we have a lot of data plane features, a lot of supported offloads, a lot of capabilities. So we're going to kind of go through these in a little more detail. There are a couple learnings that we need to take out of this. Not all hardware features that we've built over time have worked as well as we wanted them to. And a key example of that is TCP chimney offload. Today, you will not find us talking much more in the future about TCP chimney offload because, frankly, in our experience, it's caused more problems than it's solved. So we don't recommend it. If it works for you, that's great, but we think there's better solutions. Secondly, not all vendors are created equal. We wish they were in many ways, but they aren't. But we also are not going to talk about what vendors do what in better than others because each of them has their own strengths. Each of them has things that meet people's needs better. And so we'll go through that. Okay, we're going to talk about the data plane features. We have the Hyper-V switch. We have NIC teaming. We have software VRSS. Within the switch, we embed things. We can have an extensible switch. So in the R2 model, we can extend it with things like Cisco's forwarding extension with NEC. We've got ACLs. We've got a new form of ACLs in the SDN switch. We have Hyper-V virtual networking. We had NVGRE in Server 2012 R2. And now as we move forward, well, I'm going to skip forward to the future because I got a little less time than I expected. Okay, so in Server 2016, we have two stacks now that we worry about. We have the traditional stack. This is Server 2012 R2 moving forward into Server 2016. Everything that was in Server 2012 R2 still works and still works the same way in Server 2016, unless you install the SDN extension. If you do that, we have some new features, and they replace some of the old features, and some of them are altogether new. So the base features in 2016, software VRSS has been extended to work on host VNICs. We have small enhancements to NIC teaming, like LACP slow timer. We have switch embedded teaming. We have virtual machine multi-queue. And we have the converged NIC, which allows us to have the host VNIC operate with RDMA. In the new SDN v2 extension, we have integrated ACLs controlled by the network controller. We have HNV v2 task offloads, which allow us to offload VXLAN and NVGRE as managed by the network controller again. And SDN QoS, again, managed by the network controller, which extends, and we'll have a demo on this later, extends the VM QoS capabilities and makes them more reliable. Okay, how do we manage all of this? We manage it. We continue to manage the old stack, the traditional stack, through PowerShell and SCVMM. All of that stays the same. NIC teaming is still managed by PowerShell or LBFO admin, which is what, if you use Server Manager and click on NIC teaming, it invokes a call to LBFO admin. Or you can use SCVMM. It all continues, it's all still there. The new stack, the fabric gets managed by SCVMM or PowerShell. And the physical and virtual networks make use of the network controller. There's no UI for tenant management or switch extensions yet, but stay tuned. Okay, what are the new features? How do they work? We have improved virtual networking. The new SDN extension allows us to integrate the ACLs into the vSwitch, into the VFP, the virtual filtering platform. It gives us the HNV v2, gives us SDN QoS. We get bandwidth to the VM, and we'll have a demo on this a little later on, through virtual machine multi-queue, a new technology that our NIC vendors have stepped up to. We have RDMA, converged NICs, and client RDMA, which we'll have a demo on in a little bit. And we have SET, where we've brought NIC teaming into and integrated with the virtual switch. It's no longer a separate component in the SDN stack, or you can even use SET if you don't have SDN stack. So the SDN switch extension, also known as VFP, the virtual filtering platform, is a technology that we got from Azure. It's what Azure uses in their hosts. You do realize that Azure runs Server 2016, Server 2012 R2, and moving to 2016, they run Windows Server, the same technology that you can use. So the virtualization filtering platform, or VFP, comes from Azure. It acts as a virtual switch inside of the Hyper-V switch. It is the forwarding extension. It does all the address virtualization. It does all the other functions that we need for virtual networking. It uses flow tables, and we'll talk a little bit more about that. It supports data plane policy at 40 gig plus with offloads. In fact, we'll see today 50 gig coming through the switch and faster. We've seen well above that in our own labs. And, of course, it's available to you in your private cloud servers with 2016. Customers asked for VXLAN. Why? Because it's kind of the industry norm. We said, great, we're not into fighting battles. We'll deliver what customers want. So we have VXLAN. All the H&V policies get handled through the network controller, through the host agent, as Jason was talking about, and programmed into the virtual filtering platform. Virtual machine multi-queue. Most of you are familiar with VMQ, right? Anybody? Hopefully. VMQ is great. It gave us one set of queues. With virtual machine multi-queue, we get multiple queues per VM, which gives us much accelerated performance. In fact, we're going to kind of walk through that steps. The very first technology we had that made use of queues in the NIC was RSS. RSS worked very simply. As each packet arrived, we calculated the tuplet's hash, we modulated on the number of queues, and we distributed it to that queue. What this did, because every packet within the same flow would generate the same tuplet's hash, meant that every packet from the same flow ended up in the same queue, so we didn't get any misordering problems. And we could spread the queues across multiple processors. We could assign each queue to be processed in a different core. By doing that, we get good parallelization, and we get very high performance in the server. But then when along came virtualization, and we reused those queues in the NIC, and we said, now instead of doing it one per hash, we're going to do it one per VM. And so we began to say, OK, as each thing comes in, we look at the MAC and VLAN, we separate that into the right queue, we deliver that up, and we get a queue per VM, so we can assign that queue to a core. Each VM's traffic gets processed in a different core, and we get massive parallelization again. But the NIC vendors came along with some great new technology by putting a switch on the NIC. Now, instead of using just the queues in the NIC, we had ports on a switch in the NIC that we could drive. The user interface stayed the same. It still looks like VMQ. But in fact, what we're using isn't queues anymore. It's the switch ports. Or you could think of it as each switch port has its own queue. Each switch port delivers the traffic into that queue. Each queue is still affinitized to a CPU, a core, and we can deliver still that parallelization. And we can take advantages of other features in the switch. In Server 2016, we took the next step. Well, in Server 12 R2, we took the next step, which is to, in the host, as we unloaded the queues, we calculated the tuplet's hash, and we distributed it across multiple CPUs. So we could unload each queue and immediately redistribute it in software into more processors. And then we could put it into the different LPs of the VM. So now each VM could receive more traffic because it got parallelization across its LPs, its logical processors. Then we moved it to hardware. In 2016, our vendors support the concept of taking the NIC switch ports, calculating the tokenless hash at the top of the port, and distributing that to multiple queues. So in the hardware, we get multiple queues. We unload those directly to multiple LPs, multiple CPUs, cores in the host. And as we do that, our ability to deliver more and more processing increases. With that, I'm going to turn this over to Gaurav from KVM QLogic, and he's going to show us a little demonstration of this.
Hi, good afternoon. So before we get to the demo, let's take a quick look at KVM's QLogic Fast Link Ethernet NICs portfolio, a broad portfolio with range of Ethernet speeds from 10 gigabit Ethernet to 100 gigabit Ethernet, ready for Windows Server 2016. These cloud-ready NICs with pretty advanced capabilities offer a whole slew of offloads that Don presented earlier. All those offloads with some unique capabilities, such as universal RDMA that extends the choice to customer of RDMA transport that suits their environment, can be iWarp or Rocky V2. To deploy SMB direct, storage spaces direct, SET, switch embedded theming, anything you want to virtualize, workloads, all sort of offloads, including SAN offloads to save you precious CPU cycles that you can monetize. So let's switch over to the demo. So let's see VMMQ in action here.
There we go.
OK, so here we have Hyper-V host. Hyper-V host with a VM NIC provision for this VM. Here's the VM NIC on top of QLogic Fast Link 45000 series NIC, offering 50 gig of throughput. We start off with VMQ configuration for the VM NIC. Here, from the other host, we kick off TCP/IP traffic using Chariot console. That will be received by the VM. OK, so let's see the throughput. We are looking at about over 4 gigabit per second throughput, application throughput. Well, we got a 50 gigabit NIC. The throughput is not good enough. Let's see, lost the remote for some reason.
It said it lost the remote.
Wi-Fi.
Well, you've got that one.
Right. OK, let me try to connect again real quick.
Let's see if we get it back here real quick.
All
there
right.
we go. So we're getting the 4.3 gig.
And now let's enable software acceleration by enabling virtual RSS in the Hyper-V switch. Wow, the throughput has actually more than doubled. We have software acceleration. Let's try the hardware acceleration next. So as you can see, application throughput around 10 gigabit. OK, so here we enable VMMQ. And now let's see what the throughput looks like. OK, so the throughput is now 46, hovering around 46 gigabit per second. That's near line rate, application throughput. That's the power of hardware acceleration enabled by Windows Server 2016 VMMQ feature. Thank you.
Thank you, Gaurav. How many of you are ready for nearly 50 gig into your VM? That's a feature you need, right? By the way, we've tested this with Linux VMs as well, and we get comparable throughput. So whichever one you're looking for, VMMQ has been enabled in the Linux VMs and in the Windows VMs, and it operates at comparable bit rates. We get near line rate beyond 50 gig. Okay, converged NIC. Back in Server 2012 R2, the most common configuration for people who were using SMB Direct was to have dedicated RDMA NICs and separate NICs under NIC teaming under the Hyper-V switch. I'm sure some of you have probably done that kind of deployment. In Server 2016, we moved to an integrated teaming model inside the switch, and we no longer need the separate RDMA NICs, because now we can actually offer RDMA directly on the management vNICs. Sound interesting? I hope so. The primary purpose, by the way, is it reduces cost. It allows you to cut down your NIC ports on your switch, and you still get all the benefits. For those of you who've seen the S2D sessions this week, the Storage Spaces Direct, this is the configuration that they're testing with. And they're getting pretty good performance, I think. What was it, 1.3 million IOPS on 40 gig, and something well beyond that. I don't know exactly the numbers that Klaus had in his session, but they were pretty substantial. Okay. We have to manage that QoS, right? We have to manage that RDMA traffic away from the TCP traffic. We do that by making use of DCB, and then that helps us to separate the RDMA traffic from the VM traffic, but then we also have to separate between the VMs. Before we get into the bigger discussion on QoS, though, I want to point out that in Server 2016 and in Windows 10, with the releases that have been coming out in the last week, Windows 10 now supports RDMA as well. And so I've asked Bob Dugan from Chelsea to come up and give us a quick demonstration of a Win 10 client using RDMA to access data that's on a Win 10 file server. Windows 2016 file server. The question comes up all the time, why, what would you recommend, Rocky or iWarp? And the answer is, it depends. There are advantages to both. If you look inside of a data center like Azure, and you've got full-time networking engineers who know what they're doing, Rocky's a great solution. However, our #1 customer complaint with RDMA is it's too hard to configure. So we have this little slide that talks a little bit about why you might want to consider iWarp. Perf, comparable. It uses existing infrastructure. You don't have to go and configure all your switches. It just works. It's just TCP in the network. So simple setup, inexpensive, well, comparable anyway. And TCP is, pretty common. Everybody understands it. Diagnosing a TCP flow is something that people are used to doing. So this is pretty straightforward. The key thing here is if you're in a data center, either one works well. But as you extend that RDMA out to your client space, if you're going out for those people who need big files moved around, they're doing video editing or big massive data sets that they're playing with, those people need to be able to do things in a simple manner without having a network engineer in every facility. And iWarp gives that capability. Bob, why don't you show us what's up?
Sure. Hello, everyone. I'm Bob Dugan from Chelsea Communications. I'm a program manager. On this slide here, what we have is our offerings of all the things that our NIC can do. That includes not just RDMA, we also do iSCSI offload. We do FC over E offload, if any of you use that. And with RDMA, of course, we do SMB direct with iWarp. That enables things such as storage replica, so you can do multi-hop cross campuses through various switches and routers. We also have a new product out that's the next generation called T6. That's the next generation chip, our 6th generation. And on T6, we have added a speed bump. T5 currently does 10 and 40 gigabits, and T6 now does 25, 50, and 100 gig, and that's generally available next month. It's generation Gen 3 by 16 for the 100 gig adapter. And finally, one of the things that we have done is we've done a crypto engine in T6. So currently, we're working on the software for Windows and other operating systems, but it does TLS offload SSL and IPsec. And you can do it as a look-aside, so you can use it as a crypto engine, not even use networking, or you can use it inline, even up to 100 gigabits. So with that, I think I could do my demo. I'm on number 6 here, so. All right. So, oh, there was another slide that showed the configuration.
Yes,
well, it's not important.
I was trying to get to that, and for some reason the clicker wasn't, there we go.
There we go, okay. So the demo is this. So I have 2 clients here and a server. The server has 5 NVMe devices in it. It's kind of a high-end system. The demo is only with one of these 2, the 40 gig one. I'm just showing the 10 gig just to show that multiple clients can connect to the server side. Okay, now to the demo.
Okay, now to the demo.
Okay, so what I'm going to do here is I'm just going to run this script that's running disk SPD, disk speed. And let's see, this should show the 10 gig line. And as you can see up above, it's running right here, somewhere around close to line rates.
Yep.
30.
39.2 gig in a Win 10 client?
Yeah. So this is running Windows 10 Enterprise. It also can run on Windows 10 Pro. So this is the kinds of things you can do for video editing, CAD/CAM, oil, gas, or if you're an extreme gamer, perhaps, I don't know. Anyway, that's the demo. Thank you very much.
Thank you, Bob. Okay. By the way, as I told the guys inside Microsoft, this justifies you going to your manager and explaining why you need a 40 or 50 gig port on your desk. Because we all know that the next time, if you're a dev, you need to download a VHDX or something from the common file server, you'd much rather not have to wait all night. And with RDMA, it's not even going to chew up your CPU while it's running in the background. By the way, that 40 gig uses about 5% of a typical CPU. That's all it takes. 1 second here. I've got to get my machine back to life. Okay, SDN QoS. I mentioned earlier that inside the VFP, managed by the network controller, we do QoS. It's a replacement for the old VM QoS. This allows us to do much more fine-grained QoS management than we used to be able to. And so I'm going to run through a demo here in a moment that's going to show us setting some different limits on different VMs and changing them, and you'll see how quickly the network responds. It's very quick, it's very accurate, and we'll get through there. The new SDN-Quas specifically handles outbound reservations, just as VM-Quas did, but it handles it much better. It handles outbound limits. It also handles ingress limits. So if you're a hoster and you want to make sure that your people are not getting more traffic than they paid for, you can set that. And it will make sure that they don't get more traffic than they paid for. All of it, of course, managed by network controller. So I'm going to switch over here. And to start the demo up, I need to point to a couple things. If you look over here on the right side, I've got 3 VMs, Demo 1, Demo 2, and Demo 3. And at the moment, they're processing some strange stuff. There's no Quas set on this thing. So I'm going to go ahead and make sure that the traffic manager is doing the right job here. And restart the traffic generator. So we should end up with running, since we have no Quas set, we should end up seeing send rates from the VMs. Sorry. We saw a problem this morning. The VMs don't like to refresh if you don't touch them. So I got to touch them. OK, so they're all running right around 6.6. There's 20 gig available to the VMs. I've set DCB and told DCB that I've got 20 gig for RDMA and 20 gig for the VMs. So the VMs are sharing 20 gig. And you can see that they're sharing it evenly. So now I'm going to go in and I'm going to apply some Quas. Oops. OK? And we're going to start by setting it up so that the first VM gets 3.3 gigabits, the second one gets 6.7 gigabits, and the last one gets 10 gig. You can see it all settled down very quickly there. I can go in and tell it to do the opposite. So that I go 10, 6.7, and 3.3. And look at how quickly those solidified on that. Right there, right away. I can also go back in and remove the Quas. And you'll see them all go back to roughly a third. That's all the capability of SDN Quas. This is all done with the bandwidth limits. OK, a couple more slides, and I'm going to pass it over to Paul. 1, switch embedded teaming. NIC teaming is not going away. I've had so many questions of, oh, well, are you going to get rid of the NIC teaming when you've got set? Not in the short term, that's for sure. Maybe someday we'll see. For right now, set is specific purpose of meeting the needs of people who need teaming in the vSwitch. It's targeted very much at the specific applications of this release. So it supports converged NIC. It's all switch-independent teaming. Why does it support converged NIC with switch-independent teaming? Because if you have an offload that is stateful, you have to be able to drive the traffic back to the NIC where the state is maintained. And only switch-independent teaming can do that. If you use any of the switch-dependent teaming solutions, you have no management of the incoming traffic. Long-term direction, we expect to eventually put a lot more of NIC teaming functionality into set. So longer term, look for continued growth in this area. So Server 2016 is the V1 for integrated teaming. There will be V2, there will be V3. What does switch embedded teaming do? You can read the slide, I don't need to read it to you. Some of the key things are that it only teams 8 ports. If you remember, NIC teaming supported 32 ports. We haven't found anybody in the target audience for set, which is the 10 gig and above market, that needs to run more than 8 NICs in the box. If you need more than 8 10 gig NICs, you might want to swap over to 40s or 50s or 100s. OK? Also, in this release, all the team members have to be same make and model. And that's just because the work to make it do the compromises that have to be done when you've got multiple different vendors, NICs, and multiple drivers with different capabilities wasn't in this release. I mentioned earlier we've got two stacks. We've got the traditional stack coming forward. We have the new SDN V2 stack. And this just talks a little bit about which features are in which one. I'm going to leave this here for you to review later when you see the video or when you download the presentation later. This will be useful to you then. Okay? Paul.
Thanks, Don. So my name is Paul Long. I'm a senior PM, and I own time. I like to say that out loud. It sounds pretty grandiose. How many folks are interested in time accuracy? Anybody in the audience? All right, a couple of you do. Good, good. So we made some improvements for you. But first, let's talk about why does time matter? Why is it even important? And I know you guys know this, but this is what we're focusing on. And if we're missing something or there's some scenarios you think we should focus on, you can get in contact with me, and I'd like to talk to you guys personally. We talk about the financial and the banking area, and this is kind of our prime motivation for increasing the time accuracy with Windows Server 2016. There's regulations in both the EU and the US, and basically it's forcing us at the EU to be 1 millisecond accurate. And so that's what our target was. There's also regulations around UTC traceability, which we discuss in a white paper we released earlier, and I have a slide pointing to that. We've also updated the blog this morning. For information technologies, for IT, there's lots of reasons why it's important. There's also manufacturing, where we got to worry about diagnostics and monitoring, healthcare, retail, for CPI, credit payment industry, and online sales. And there's other industries or other areas as well. So these are all areas we're thinking about. Again, if we're missing something, let us know. So let's discuss the improvements. And I'm moving pretty quickly here to try to get us all on our airplanes before they leave without us. We basically have the latest generation NTP time synchronization. So we have better statistical processing and improved error correction. And with this, in our domain, we're able to see a 500 microsecond accuracy in the domain, at the domain level. And I'll kind of have a slide on that, more details later. We've also been able to distribute this accuracy to guests. And so we have this new version of this VMIC protocol, which again have a lot of details in the TechNet article. But this allows us to get accurate time. And so I have a 90 microsecond accuracy, and this is from the guest to the host. So that sort of accuracy allows you to get this 1 millisecond accuracy across the domain. We also have a transparent stratum, which just means now the host and the guest communicate the stratum accurately, where before we used to have a fixed stratum, so we fixed that in Windows 2016. And then we also have some better monitoring, some perfmon counters that you can use to baseline, determine your accuracy, and also do remote monitoring. So these are all new things in Windows 2016. So the next slide is a kind of a trip through the domain, just to sort of kind of understand how this works at a high level. And the first thing I'm going to point out is that in order to get this accuracy, it's not going to come for free. You need a highly accurate stratum 0 level clock. So this means either a PCI card or a time appliance. That is a requirement here. You can't, if you don't have good time upstream, it's not going to be, it's only going to be amplified and be worse downstream. So you can't just set it out to, some website and expect to have good time. You're going to need a solid time appliance or hardware. And so when we look at the time in Windows 2016, at that first layer with the device connected to it, I mean, obviously we should get good time. We're talking a 5 microsecond offset, or a 5 microsecond skew, and we're looking for a millisecond, so we're pretty good there. Now when we go to the next level, the next kind of high-level point here is your network and your environment have a lot of effect. So you can't just expect to deploy this and to get 1 millisecond accuracy unless your hardware's up to the task. Now, we're not talking about special hardware or anything, but if you have lots of hops between your computers, the hops are going to affect your accuracy in the end. And so at this next layer, where we're talking about 1, 2, 3 hops perhaps, we're talking about a 50 microsecond skew. So again, we're well within our bounds of 1 millisecond. Now let's talk about Hyper-V host, because we can also push this accurate time down to your virtual machines. At this edge of our domain, now we're talking a 500 microsecond skew. And so now we're even more hops, but we're still within a regular domain setup. Again, nothing special here. And then when we talk about the hosts running in the virtual machines, we can talk about Windows machines or Linux boxes as well. We have a Linux fix that we have in the distribution, or going to be part of a distribution as soon as it goes up the chain. So this is available to Linux VMs as well. It's not just limited to Windows. And the VMs do have to be 2016 or Windows 10 anniversary. That is a requirement here. But what we're seeing there, again, is basically this small offset between the host and the guest doesn't really affect our measurements. So we still see a 500 microsecond skew. And this is even with a load on the VM. So with a 75% load on the virtual machine, or on the host machine, we can still maintain this accuracy. Now, I mentioned a couple of points here. VMs can be DC for the host partition. So there's cases where you can have loops. There's just, I think, certain cases you need to pay attention to. Hypervisor is just another VM, and it gets time sliced. However, with this fix that we've done to the Hyper-V, you used to have this solution where you have to disable the time sync service from your guest machines, and you no longer have to do that with Windows 2016. So this is a change that you used to have to deploy as a workaround before, and you don't have to do that anymore. So in general, with Windows 2016, you can deploy accurate time throughout your domain and meet this 1 millisecond regulatory requirement using the simple setup of a domain. As long as your hardware and your network can handle that, then you can deploy and get this accuracy. Here are some links, and this is the links I was talking about to the first ones. The WS 2016 time is the TechNet article. There's also a video I'm working on. It hasn't been released yet. I didn't have a chance to release it, but just remember that'll probably be available next week. And then we've updated the blog this morning with this information. And here's my email address. So if you guys have any specific questions, or if you want to talk to me about your time, let me know, and we'll talk further. And that's the end of my talk. Thanks, guys.
Thank you, Paul. Jason's joined me on the stage as well. There's 2 mics for the audience to use. If you've got any questions, we'd be happy to entertain them. Let us know, who you want to answer the question, and we'll try to get it answered.
Any questions?
Any questions at all?
Anybody late for their plane? No?
All right, well, if there's no questions, we'll go ahead and bring us to a close. Thank you very much for coming to this. We know that staying to the last session of the last day of the conference can be a little bit challenging for some people, and we really appreciate your willingness to come and hear this, and we hope it's been interesting for you.
Thanks, Eric.